Hello guys, we are from the third team. We are gonna present about chapter 4, preliminary design. That about steel and concrete composite bridge design and guide. Our team is, this is our member. The first one is,
My name is Ahmad Absar and my lesson RP is 52.
And then my name is Alivia De Febrianti. My last NRP number is 053.
My name is Bagus Subakti. My last number NRP is 054.
My name is Afian Rifki. Last NRP 055.
Okay, my name is Muhammad Fernanda Firmansyah. My last NRP is 057.
and last, my name is Ishak. My last number NRP is 58. Okay, let's to the topic. This one we gonna with Agil.
Okay, first is general. In the preliminary design stage, the bridge designer develop a structural solution based on the client requirement. There are outlined in the design statement in accordance with the bridge manual. It is recommended that consultation with other representatives of the bridge industry, such as fabricator and coating supplier, should be conducted at an early stage as they will be able to provide advice on optimizing the bridge design. This will increase the efficiency and cost effective of the steel concrete composite bridge option. And design for construction. While minimizing cost may be the most obvious consideration when embarking on the design of a highway bridge, the health and safety of all those concerned in the construction of the bridge and in its maintenance throughout its life is the responsibility of all decision makes relate to the procurement of the bridge, as well as aiming for structurally efficient solution. The hazard associated with the construction process must be fully appreciated from the outside. Steel work fabrication. Clean line in the overall appearance and minimum use of complex detail are most likely to lead to an economic and efficient bridge structure. Two external constraints of the compromise selection of the best structural solution. The fabrication of the basic I section is not expensive, especially with the use of modern semi-automatic girder welding machine, T&I machine, such as that shown in figure 4.1. Overall fabrication cost is the same order as the cost of the material used, with the widespread use of computer in design and in control of fabrication shop machines. Geometrical variation such as curve soffit, varying super elevation, plane curvature, and pre-assembly can be readily achieved with reasonably minor cost penalties. Much of the total cost of fabrication is incurred in the addition of stiffener, the fabrication of bracing member, butt welding, the attachment of ancillary item, local detailing that leads to a significant manual input to the process. Okay, this is the figure. Next. The designer can exercise freedom in the choice of overall arrangement, but should try to minimize the number of small pieces that must be dealt with during the fabrication process. Welding required not just for forming the plate girder, but for all other welded component and connection in the structure must be considered and designed carefully. Inappropriate detail or the specification of an over design weld detail may result in a substantial increase in the fabrication cost of the structure. Fabrication advice should be obtained directly from fabricator to assist in the choice of detail at an early stage in the design. Most fabricators will come approach from designer and respond helpfully to questions about fabrication method and require for advice about optimization. Transportation by road imposes certain limitation on the size and weight of fabricated assemblies. The most frequent not limitation is a maximum length of 20 meter, above which special notification and procedure apply. Nevertheless, fabricators in the New Zealand are used transporting longer loads, whereas exceptional case getting well over this limit have been transported. Further guidance on the transportation limitation is available in Guide to Heavy Vessel Management. Next.
Next, erection scheme. Construction of a composite bridge superstructure, usually processed by the sequential erection of the steelwork, working from one end to the other, depending on the type of jacking used. This is followed by concreting of the jack slab and removal of false work for in situ jacking, or alternative by the placement of partial depth precast jacking followed by an in situ or of the remainder of the jacking. It is much quicker to establish a secure connection using both than by welding. On-site welded chains are more expensive with a high risk of delay due to weather and even rush for quality control on a small job, but welding may be considered on large jobs. The stability of girder during erection and under the weight of wet concrete will have a significant effect on the sizing of the top flange in midspan region and to a lesser extent on the bottom flange adjacent to intermediate support. General guidance on the erection of bridge steelwork is given in the BGSI Guide to the erection of steel bridge BGSI 2005. Next, slab construction. The deck slab of a composite bridge is normally cast in situ on either temporary or permanent formwork. Recently, the use of permanent formwork used a partial depth precast concrete decking has become common. The latter avoid the costly and potentially hazardous operation of stripping out temporary formwork after casting. Partial precast decking can be used for slab spans up to about 4 meters. They are placed on the girder flange edge, allowing the connecting shear stud to have a solid concrete block to assist in transferring the longitudinal shear force between the steel and concrete. This is the type of partial depth precast decking considered considered in this quiz. NZS 3101 Concrete Structure Standard and SNZ 2006 also prohibits the use of the common panel-to-panel connection in high fatigue location, such as traffic loads, unless there is performance verification. This is full depth precast decking joint style, not discernible. Next, slab construction. All publicly owned bridges are designed for 100-year design life as stated in the bridge manual and are assumed to be provided with periodic maintenance as contemplated in NZS 3404.1 Steel Structure Standard NZS 3404.1 SNZ 2009 NZS 3101 and SNZ 2006 and the coaching standard AS NZS 2312 SNZ 2002. The design and in particular the detailing should recognize the need for durability and calculate whatever maintenance will be necessary. Particular issues to be addressed include access for repainting, detailing requirement of their drainage arrangement so that minimal maintenance is required and their failure will not cause durability problem. Facilities for breeding replacement. The research mentioned at 1991 RMA regulation require the assessment of hazard during maintenance work. The design must be such as to avoid or reduce as far as practicable risk during maintenance without minimizing environmental impact or considering the health and safety concern of the maintenance personnel.
Choice of structural configuration. For a typical highway project, the choice of bridge type will be between a multi-girder and a leader deck configuration. The advantages of a leader deck configuration are a reduced tonnage of steel relative to a multi-girder deck as a result of the best possible load share in the case of a leader deck. Although fabrication cost per ton may be higher, will switch to efficient slab construction, uniformity in thickness easily detailed to switch precast permanent from work and full with placing of concrete. Cross girders provide regular stiff restraint to cantilever construction facilitating the use of precast cantilever units where horizontally curved girders are needed The regular spacing of cross girder easily provides the restraint to the bottom flange. Only two columns need at each intermediate support, avoiding leaf piers and achieving a more open appearance. Reduce maintains liabilities. Less surface are of steelworks, fewer small bracing elements, and fewer bearings. Faster construction time provide additional cost saving to the project's total cost. The advantage of a multi-girder configuration are smaller piece size of mine girders, thus reducing crane requirements. Brace pair of girders require no additional temporary bracing to top flange. Fewer bolt connection on sides. Good load distribution through transverse bending of the slab. Readily adaptable to any bridge with shallow construction depth can be achieved without resorting to excessively large flange plates. Influence of substructure constraints. As mentioned in section 3.5, it is recommended that the substructure design is considered at an early stage. The form of the substructure at intermediate supports whatever portion of appearance of constructions. Often has a strong influence on the form of the superstructure. For example, a low clearance bridge over poor ground might use multiple main girders on a single port pier, whereas a high-level bridge of the same deck width and span over good ground might use a leader deck with twin main girders on individual columns. Influence of scale. Highly skilled bridges are sometimes unavoidable, but it should be noted that the high scale leads to the need for a greater design effort, more difficult fabrication, and more complex erection procedures. In particular, that analytical model, the detailing of abutment, trimmer beams, pre-cambering, and relative deflection between main beam must all be considered carefully. Influence of requirements for drainage. Drainage of the roadway on the bridge can often be achieved solely by drainage channels on the bridge deck, but drainage runs might also be required below the deck slab. Arrangement for such drainage run may will influence that position of main girders in the cross section and possibly in the detailing of cross girder of intermediate bracing.
Okay, and then the next topic is preliminary sizing and material selection. We are going to study about steel. Okay, the main structural steel member for bridge are usually grade G300 or G350. Higher strength steel grades such as G450 L15 are available and can be used in design, but they are more expensive. When processing design bridge girder, designers should account the available steel plate for dimension and to minimize wastage and optimize the girder size. For this case, There are two examples of solution. Number one, cutting the maximum number of flanks out of one plate to minimize wastage. This will assist in keeping the fabrication in cost low. And number two, choosing the web depth based on the available plate width. And then note that when the plate is cut, the designer should allow for 10 mm loss for each cut and take into account the pre-camber allowance. It is recommended the designer discuss this matter with fabrication to ensure the appropriate plate dimensions are used at the detailed design stage. And for bracing member, hot roll section angles, channels, and I section may be used, especially angle for K or X brace. If weathering steel is to be used, there are no available hot roll section. However, fabrication can fabricate similar section from plate. Seek advice from a fabricator about what sections are economically feasible. Guidance on availability and delivery times for specific products should be sought from fabrication or steel supplies as nearly as possible to optimize the final bridge girder design. If the construction period is limited, delivery times might affect the choice of component. And then the next topic is concrete. The choice of concrete depends on infraction. For example, for above-ground substructure components such as abutment beams, pierhead beams, and piers, we can use 40 MPa concrete is common. And then for slab decking, 50 MPa is usually specified for precast decking and when durability aspect govern. Example, the bridge is located in marine environment, while 40 MPa concrete is specified for in-situ decking and topping. All concrete components, whether in situ or precast, are manufactured in accordance with NZS 3104 specification for concrete production, constructed to NZS 3109 concrete construction and designed to NZS 3101 SNZ 2006.
Okay, the next topic is preliminary design, sizing, and multi-girder bridge. Okay, this is the figure 4.6. This is figure about typical span or the proportion for continuous span in multi-girder bridge. Okay, the next topic is girder spacing. The total transverse moment in the slab of a multi-girder deck are not particularly sensitive to girder spacing in the range of 2.5 meters to 3.8 meters. The increase in the local moment with span is more or less balanced or by a reduction in the moment arising from the transfer of load from the one girder to the next girder. It is advantageous to choose the widest girder spacing as possible, consistent with all the geometrical consideration and with the appropriate decking option, such as partial depth precast decking outlined in section 2.3. In preferable to use an even number of girders so that they may be paired during construction, but an odd number can be used in due provision is made for the erection of single girders. In selecting a suitable girder spacing, attention must be paid to cantilever at the edge of the deck. The cantilever length from the outer girder center line should normally be restricted about 1.5 meters to 2 meters, including the edge beam when designing for accidentally traffic load applied into barrier. The length of the cantilever may need to be restricted and the slab increased in thickness locally. The next topic is girder profile. For simple span over about 25 meters, a construction depth top of slab to underside of beam of between about 1 per 18 and 1 per 13 of the span can be achieved with fabricated beam. Although the most economically solution will be toward the deeper and this range. Note that the cost of applying a protective coating system must be considered as the cost may increase with the increased surface area of a deeper beam in comparison with a shorter beam. For shorter span, the depth is likely to be proportionately greater, particularly for span under 20 meters. This may limit the use of a welded beam due to the available depth in the comparison of to a fabricated beam. For the composite continuous span with parallel flange, the constructor's depth gain from the top of slab to underside of beam is typically between 1 per 20 and 1 per 25 of the Mayer span. The use of curved or tapered haunch can be reduced construction depth at midspan at the expense of increased depth at the internal support. A selection of typical arrangement is given in figure 4.5. Okay, the next topic is flange and web size. Experience and a few rules of thumb can often be used for an initial selection of size. As a result of the weight of the steelwork contributing little to overall designing moments, the selection can be quickly refined. One such set of simple rules is given in Appendix C. Spans that must be fabricated with more than a single length to main girder, the opportunity to the ferry girder make up in the different pieces required for each span. The maximum length of the piece is influenced by transportation. Load over 20 meters long requires special arrangement and the length of the plate that is available. Next is slab thickness. For initial design, choose a slab thickness of 215 and 50 millimeters. This can be refined in detailed design. In the cantilever barrier designed for an accidental traffic load, use an initial thickness of 330 millimeters for 2-meter cantilever at the root of the cantilever, reducing to 250 millimeter at the first internal male girder.
4.7 Preliminary sizing ladder decks. 4.7.1 Girder spacing. The main girder spacing should be such that cantilever are about 1.2 meter to 2 meter long. Main girders are typically spaced between 5.5 meter and 18 meter, apart to suit the root width. For a wider deck, use either two spirit ladder decks or two sets of ladder decks still work with a common slab. If very high containment barriers have to be provided at the edge of the deck, choose a shorter cantilever or thicken the slab. 4.7.2 Girder Profile. Main girder are usually of uniform depth, although hunch girder may suit some situation. For uniform depth girders, the overall depth should normally be between about 115 and 125 of the major span. For wet decks, the dip should be towards the deeper end of the range. 4.7.3 Flange and Web Size. Choose initial flange size on the basis of previous experience or using simple line beam models. Four point 7.4 Slab thickness. Choose a slab thickness of 250 millimeter for a cross girder spacing up to about 4 meter. With do regret to cover required for durability. With do regret to cover required for durability. Where a very high containment level barrier is to be carried, there will be large moment and lateral force to be sustained, with consequence on slab thickness.
Okay, guys, that's all is our presentation. Thank you for your attention.